Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers. Last time, we left off wondering how imaginary numbers could help us find the roots of our equation x squared plus 1. And further, how imaginary and negative numbers even became part of modern mathematics after being avoided and ignored for a couple thousand years, because, let's be honest here, they don't really make that much sense. But something happened in Europe around 5 centuries ago that would no longer allow mathematicians to ignore these numbers. An Italian mathematician, Scipione del Ferro, was trying to solve a problem not that different than ours. At some point, you've probably seen the quadratic formula. This formula is super useful because it gives us the roots of any equation with a highest power of 2. All you have to do is plug in a, b, and c, and out pops the answer. Del Ferro was trying to find a formula like this for equations with a highest power of 3, cubics. The general case is pretty tough, so Del Ferro first considered the case where the x squared term is missing and the last term is negative. In the 16th century, negative terms were way too sketchy to write, so Del Ferro wrote his cubic as x cubed plus cx is equal to d, and required c and d to be positive. Now that we have our equation set up, the game here is to get x by itself on one side, and all the constants on the other side. This is pretty easy in linear equations. We can just add, multiply, divide, or subtract until we get x alone. Quadratics make this a bit harder. You may have learned how to solve these in school. It requires some cleverness and factoring by completing the square. Del Ferro was trying to do the same thing for his cubic equation, and through some clever substitution he eventually found a solution. Just like the quadratic formula, Del Ferro's new formula allowed him to find the solution to cubic equations by simply plugging in values. Now, for some reason, the way mathematicians earned money in the 16th century was through challenging other mathematicians to what were basically math duels. So Del Ferro kept his new formula a secret to use in his next duel. What happens next is a bit of a long story. Here's the quick version. Del Ferro kept his formula secret until he was on his deathbed when he finally told his student Antonio Four. Four immediately thought he was invincible, or at least invincible in a math duel, and challenged a way more skilled mathematician, Fontana Tartaglia, to a duel. Tartaglia had already claimed he could solve cubic equations like this, but had actually been totally faking it. Tartaglia freaked out before the math off and actually figured out how to solve these equations at the last minute and proceeded to completely dominate Fior. Tartaglia then went on to share his formula with the world. Not really, he kept it super secret so he could keep kicking butt in math duels. That is, until a very talented mathematician named Cardan heard about the formula and pressured Tartaglia to share. He eventually went along, but only after Cardan swore to an oath of secrecy. Fortunately for us, after Cardan came across the surviving work of the original discoverer, Del Ferro, he figured that it wasn't such a big secret and published the formula in his book Ars Magna. Cardan went on to improve his borrowed formula, even making it work for cubics that included an x squared term. However, along the way, Cardan came across a problem. In a slightly different version of the equation, written as x cubed equals cx plus d, under certain values of c and d, the formula would break. Let's take the innocent-looking equation x cubed equals 15x plus 4. When we plug into Cardan's formula, we get a result that involves the square root of negative numbers. The square root of a negative number created enough of a problem to stop Cardan in his tracks. Square roots ask us to find a number that, when multiplied by itself, yield the number inside the root sign. The square root of 9 is 3 because 3 times 3 is 9. Importantly, the square root of 9 is also negative 3, because negative 3 times negative 3 is also positive 9. But what about the roots of negative numbers? What is the square root of negative 9? Positive 3 won't work, and neither will negative 3, so we're stuck. Cardan was stuck too. He didn't know of any numbers that, when multiplied by themselves, resulted in a negative. Now, this certainly wasn't the first time the square root of a negative had shown up. Usually mathematicians would interpret this as the problem's way of saying there are no solutions, and in many cases this is true. However, in this case, we know there is at least one solution because of the way cubics are shaped. Regardless of their coefficients, cubic functions will always cross the x-axis at least once. meaning that our equation, x cubed equals 15x plus 4, will have at least one real solution. So what we have here is a problem that must have an answer, and a formula that has been proven to work. But when we put these together and try to solve the problem with our formula, we quickly arrive at what appears to be the impossible: the square roots of negative numbers. Sometimes when things break in math and science, it means just that, they're broken. But there are other more interesting situations in which broken mathematics gives us the keys to unlock new insights. The way in which Cardon's formula was broken turned out to be incredibly important to mathematics and science, and that's what we'll discuss next time. We left off last time with Cardon and his broken formula for finding the roots of cubic functions. Cardon knew that his problem had to have a solution, but didn't know what to do with the square roots of negative numbers that kept popping up in his equations. Cardon came close to finding a way to make his formula work, but got stuck in an algebraic loop where a bunch of work would just lead him right back to where he started. It took one more generation of mathematicians to get to the bottom of this. Cardon's student, Raphael Bombelli, made some incredible insights about what's really going on here. Let's remember why Cardon was stuck. The square roots of negative numbers ask us to find a number that when multiplied by itself will yield a negative. Neither positive nor negative numbers will work. Bombelli's first big insight was simply to accept that if positive numbers won't work and negative numbers won't work, then maybe there's some other kind of number out there that will. Now, if there is some other kind of number out there, a good follow-up question is, what are we going to call it? After all, we need to use it in our equations. Bombelli's approach was a very practical one. Rather than dream up a new name and symbol, Bombelli simply let the square roots of negatives be their own thing. In the past, mathematicians would have thrown in the towel here and declared the problem impossible. But Bombelli was able to press on simply by allowing the square roots of negatives to exist. Let's take a simple example of our new numbers, the square root of -1. For being a new kind of number, it doesn't look very exciting, and might kind of seem like our old numbers. But remember, it does have the exact special property we need. When we square it, the result is negative. Further, since our number doesn't behave like a positive or a negative, it must be something new. Now, if this all seems a bit fishy to you, like a slightly too convenient algebra trick, you're in good company. In fact, it's hard to introduce imaginary numbers without them sounding like an arbitrary invention. However, before we dismiss the square root of -1 as some abstraction invented to torture students, let's review what we've learned so far. Cardon and Bombelli were genuinely stuck on a tough problem that they knew had a solution. What Bombelli was able to see is that if he extended the existing number system, as had been done so many times before, he could solve the problem. Just as people needed fractions, zero, and negative numbers to solve new problems in the past, to solve this problem, Bombelli now needed the square root of -1 to be its own brand new number. Let's make sure we're clear about what it means for the square root of -1 to be its own number. If our new number is truly a discovery and not an invention, it should behave like the other numbers we already know about. It should follow the established rules of algebra and arithmetic. And it turns out the square root of -1 does, for the most part. Just as we can split apart the root of the product of two positive numbers, we can also split apart the square roots of negatives. The square root of -25 splits into the square root of 25 times the square root of -1. This process is important because it allows us to express the root of any negative using the square root of -1. The square root of -25 becomes 5 times the square root of -1. We can use this process to expand the root of any negative number, writing it as some number we already know about times the square root of -1. Let's quickly make sure that our new numbers follow the same algebra rules as our old numbers. In algebra problems with x, only like terms can be added and subtracted. 2x plus 3x is 5x, but 2 plus 3x is just 2 plus 3x. Likewise, 2 square roots of -1 plus 3 square roots of -1 is equal to 5 square roots of -1. But 2 plus 3 square roots of -1 is just 2 plus 3 square roots of -1. Finally, unlike terms can be multiplied, just as in algebra with x. 5 times x is just 5x, and 5 times root -1 is just 5 roots of -1. Now there are some cases where our new numbers behave a little strangely, but these can often be avoided by first separating out the square root of -1. Now that we have a grasp on how our new numbers work, we can see how they fix one of our problems from last time. We now have a strategy for dealing with the roots of negatives. We can evaluate the square root of -9 we were stuck on and obtain 3 times the square root of -1. All this is important, but it isn't enough to solve Cardon's problem. we still need to figure out how to deal with the cubed roots of these numbers. Bombelli was able to solve our problem through one more powerful insight, and that's what we'll discuss next time.